Hello, everyone, and welcome to the Satellite Book Club Seminar Series. Brian Gockel here, Office of Observations, and we want to introduce the subject of our talk today is GLM Lightning Observations from the May 30th, 2024 Supercell near Midland, Texas. Our speaker and presenter today is Joseph Patton, Faculty Research Assistant from CSES, and our facilitator today is Rick Lujan, Senior Meteorologist and IMET from NWS Midland, Texas. Just a few reminders before we get underway. This session is being recorded, and there's a pinned message in the chat about OCIO Privacy Act guidelines. The Q&A session will be after the talk as usual. We encourage attendees to post their questions in the chat room as they'll be fielded from there. If you're logged in as an alias account, please sign in with your full name or specify your full name when asking a question in the chat. As usual, we're looking for future presenters. We're looking forward to working with you. If you're interested in giving a talk, the TowerS team has put together a form. Emily just dropped it in the chat. Nice user-friendly form to sign up to be a presenter or a facilitator. We're happy to work with you. In fact, we encourage it. The training team can help create or update training materials that may be unavailable or out of date. Please contact Ross Van Til for information or questions about that if needed. Thanks, as always, to the Chief Learning Officer, as well as the GOM Leo programs, our facilitators, and all the participants today. Joseph, before we turn the mic over to you, just a little bit about Joseph's background. Joseph Patton is a faculty research assistant at the Cooperative Institute for Satellite and Earth System Studies, CSES, at the University of Maryland, College Park. His work focuses on creating training materials, conducting outreach to end users, and analyzing observations from the geostationary lightning mappers aboard the GOES-R series. He previously served as a meteorologist with the National Weather Service in Midland, Kansas. Joseph, welcome back to the Satellite Book Club.
Thank you so much for that introduction, Brian. And we'll go ahead and jump right on in. So before we look at any satellite observations, I want to talk about this specific event and walk you through some of the factors leading up to the observance of some of the severe weather from the supercell. So starting with the near storm environment, we had a loaded sounding from Midland, Texas at 12Z that morning. And we already see we've got steep mid-level lapse rates on the order of 8 degrees C per kilometer. And we have got most unstable Cape values over 2,000 joules per kilogram. And the reason why I'm showing the 12Z sounding and not the 0Z sounding is by the time we got to 0Z, the severe weather was ongoing and they were not going to launch an evening sounding and put their personnel at risk. So one thing I wanted to note here too is that we have on the surface analysis from WPC at 21Z, we have a low pressure system or minimum in the southeast corner of New Mexico with a very strong dry line draped over the Big Bend region of Texas. One thing I wanted to note is that you can see there is a 66-degree dew point to the east side and a 6-degree dew point to the west side. So a 60-degree difference in dew point. That's pretty intense dry line. So that's going to be one of our factors for initiation today. Looking at the severe forecasts from this Storm Prediction Center and some of the verification from that day, this is graphics toggling between the 1630Z outlook and the 20Z outlook, and some text from the outlook that was issued that day explains that they expanded that enhanced and slight risk to the southwest to accommodate some of the movement from outflow boundaries from previous storms, and the fact that strong heating was leading to destabilization, and with those 60s dew points, that could lead to severe storm potential. And they were right on the money with that one, because right here is where our tornado was observed that day. So looking at some of the severe events, this is a video that was taken by personnel at NWS Midland. And this video was taken at 2229Z from right outside the office, which is where the star here is on this map. And you can see that there's clearly, 80 plus mile-an-hour wind gusts. We've got hailstones greater than 2 inches in diameter, which actually ended up causing a considerable amount of damage, including to employees' vehicles in the parking lot, which were totaled, unfortunately. And this map here on the right-hand side is from the NOAA Damage Assessment Toolkit. And we can see we've got this EF2 tornado, which passed right near the office, and then later an EF3 tornado further south. So just a few minutes later, at 2245Z, we have this beautiful picture of a tornado that was ongoing. And this vantage is from Roger Edwards, who at the time was a SBC lead forecaster and avid storm chaser. And his perspective is from right about here, looking northwest towards this EF2 tornado. And so he observed this just southwest of the Midland area. Some of the tornado damage that was observed associated with this supercell, we can see that we've got, the metal siding of a large building that was damaged on the right-hand side. There were multiple instances of downed or damaged telephone poles, and we can even see that this mobile home here was destroyed. And all of this damage pictured here occurred within 2 miles of that WFO Midland office. So what did this look on radar? So this was very close to the Midland radar. In fact, Rick was just telling me earlier that there were observances of hail before they even saw any significant radar reflectivity on the lowest scan. So this storm popped up very quickly and matured very quickly, very close to the radome. And this, as you can see, the warnings were being put out as the storm really deviated to the right with its motion down towards the southeast. So there's a few interesting things that I want to point out from this radar animation. First, we can see we've got this very strong outflow boundary here, which serves as our method for initiation that gives us our forcing that leads to the supercell formation. And we've got this classic supercell structure on radar. We can see a hook echo here. We can see a strong velocity couplet right there that's rotating counterclockwise. And this is a textbook, it's even got that sort of screaming eagle shape here as it still continues to drop large hailstones. So this is just a textbook classic supercell structure on radar. So a little bit about what the Midland WFO was writing at the time. So at 2224 Zulu, they put out their first PDS warning, particularly dangerous situation. And that was from a confirmed tornado given to them. And that information was given to them by trained weather spotters. They had that considerable tag on the warning. And then just a scan or two later, the pattern is recognizable on the 2229 Zulu radar from Midland. We've got reflectivity showing a hook echo. We've got gate-to-gate shear in our velocity. And then we can also see that we've got this drop in correlation coefficient. So those together serve as our tornado debris signature. So this was able to be confirmed with radar too, as it was happening at such a low altitude for the radome. So now jumping into what some of the satellite observations look like for this storm. So I'm going to start with true color because I think that's one of the most interesting satellite products. We can see we've got this really strong overshooting top, looks like popcorn at the top for this storm. And we've got a large anvil plume spreading eastward with the main flow. And then one other thing I think was interesting too is you can see this westward progression here of the dust associated with the strong winds from the outflow from this storm. So just a lot of interesting things going on that we can see on the true color RGB. So more ABI observations, and so far these are all from GOES-East. The GOES-East had a mesoscale sector, so we were getting this 1 minute imagery from the GOES-East at the time. And then the GOES-West did not have a mesoscale sector for this particular area at this particular time. And the equivalent of the CONUS, the PAC-US sector, cuts off just to the west of here. So these ABI observations, we're just going to be focusing on the 1 minute imagery from the GOES-East, but we will also bring in the GOES-West GLM observations here in just a minute. So we've got visible here on the lower left. We've got channel 9 mid-level water vapor on the upper right, and we've got channel 13, the clean long wave IR on the lower right. So we can see that there's very moist, very cold cloud tops as seen in all these products from the GOES-East ABI. And we've got that strong overshooting top that indicates our intense updraft strength. So these darker colors here, very cold cloud tops, and then also very moist at the same time. So now combining that ABI information with the GLM observations, we've got our suite of operational GLM products here. In the top left is the flash extent density, and in the middle, the bottom left is minimum flash area, and the bottom right is total optical energy. So these, as a reminder, these GLM products are showing aggregated lightning characteristics. So of all the flashes that occur within a single pixel, you're getting aggregated information about them. So the flash counts are what's being displayed, or the flash density is what's being displayed by FAD. You've got your flash brightness, so the total amount of light in that narrow band wavelength associated with lightning is being displayed by total optical energy. And then finally, we've got consistently low minimum flash area values. And that's really what we expect from an extremely intense updraft. You know, with the vertical orientation of that intense updraft, you've got a large amount of charge separation happening in a small aerial extent. So from the satellite's perspective, even if that charge may be occurring over a large altitude, it's still a small aerial extent. So that's one of the reasons why we would expect, and that we see here, these low minimum flash area values throughout the life cycle of this supercell. So one thing I wanted to show here that I've been experimenting with is annotating these GLM values. So basically, I put a grid of points across the screen, and then I sample the MFA values at each one of these points. And if the value is below a certain number, then I put a label on that point. And so in this case, the smallest in area flashes, which is what's being displayed by MFA, if those are less than 250 square kilometers, that's notated. And then if they're less than or equal to 70 square kilometers, that's highlighted. And this is really the smallest value that you're going to get from MFA. It should be that 64 square kilometers, but there's some rounding, and I think what I was doing with the GLM processing, but essentially that's going to be your smallest value, which is just the 8 by 8 kilometers resolution of the GLM instrument. And this color map scale goes from 64 to 2000. So we can see those consistently low values in MFA throughout the life cycle of the supercell. Switching to flash extent density. So now we're going to see those annotated values here. We have put an annotation for greater than 40 flashes, and greater than 75 flashes are highlighted. So you can see some of those gold values pop up for greater than 75 flashes within that 5-minute period. And the color map here is from 1 to 128 flashes, but that's not a one-size-fits-all approach. We really encourage forecasters to change that maximum value of the FAD color map, which you can do on the fly by right-clicking on the product in your AWIP station. We encourage you to change that value as needed for the type of supercell or type of storm you're working with. So in a off-season event, you might want to use a lower color map, maybe a maximum of 64. And for an April May event, you may find that it's better information, more actionable information for you to quickly make decisions with a higher number than 128. But 128 is very close to what test sessions with the hazardous weather test bed a few years back showed most forecasters to find the best suited their conditions for warning operations. So one thing I do want to note here too is that there is a satellite parallax in both the ABI and the level 3 GLM gridded products that's resulting in a slight offset from the actual ground conditions that are being observed here. And also, just apart from satellite parallax, the greatest density of flashes, where you've got that strongest updraft, may not necessarily be where those severe events are occurring, right? So if you've got severe gusts from the rear flank downdraft, those are going to be offset from the actual location of the updraft. And if you've got a tornado, that hook echo may not be in the exact same place where you're expecting to have the most lightning flashes. So now switching to total optical energy, we've annotated here, we've got values over 200 femtojoules per pixel for 5 minutes are notated, and then 500 plus is highlighted. We can see that these values for total optical energy were actually not that high. We only see a handful of pixels show up in just a second here where we've got values over that 200 threshold. So right about there, we could see some as high as 300. And this color map scale is from 1 to 1500, which I believe is the standard scale that the NWS uses as well. So again, we've got that satellite parallax in both the products, and our greatest optical brightness from the lightning is also somewhat offset from the occurrence of severe weather, but not always. So now we're going to compare the GOES-West, which is on the left-hand side, and the GOES-East, which is on the right-hand side, values from the GLMs. So this is flash extent density, and we can see that they observe similar flash densities for the supercell, with GOES-East displaying slightly higher flash counts most of the time, but there are also some minutes where GOES-West, for different reasons, was showing slightly higher flash counts. So one of the interesting things about the Midland WFO is it's right on the line where of 103 degrees west, that line of longitude, where previous research has found that greater flash densities were observed to the west of that line for GOES-West and to the east of that line for GOES-East. So this is really one of those areas where we recommend, if you have the ability or the bandwidth, to incorporate observations from both GLMs. So there are different reasons why one satellite may see a different number of flashes from the other, and it's not always an area-based factor, and we'll talk more about that in a minute. But I just wanted to share that that's going to be something to keep in mind if you're a warning decision maker, incorporating the GLM data in this area of the central United States. So that really spreads all the way up the high plains. And then also, one thing I want to note here is the satellite subpoint is to the southwest if you're looking at GOES-West, and to the southeast if you're looking at GOES-East. And so that satellite subpoint is like if you put a dot on the ground right below where the satellite sits, and in your head you can mentally say, okay, that's the direction in which I can account for parallax by shifting these observations slightly in that direction. So now comparing the GOES-West and GOES-East minimum flash area values, just as a quick glance, we can see that there's a broad area of those minimum values, 64 or 70 square kilometers, and that was observed throughout the life cycle of the supercell by both GLMs until the updraft starts dissipating around 126Z. Right here, we can see the MFA drops off. But even as that supercell updraft was collapsing, we still were observing large hailstones 3 inches in diameter at the time. So, you can imagine that some of those large hailstones were riding that updraft for hours until finally, when the updraft collapses, all of those hydrometeors fall out. So even as the storm looks less impressive on radar, you may still be observing damaging severe events. So that's something that I thought was interesting. And then also, one other thing that you can see from the minimum flash area product is we've got large stratiform region flashes associated with the anvil crawlers. So remember, we had that large anvil region that we saw on satellite ABI observations spreading out in the eastward direction. And that's where we can see some of these larger minimum flash area values, and even on the west side as well. So some of those are associated with anvil crawlers, and that's pretty typical with intense convection. So now switching to total optical energy, our third operational GLM gridded product. Pretty similar values again between GOES-West and GOES-East. We can see we've got that brightness associated with the convective core of the storm. And the values in GOES-East are again slightly higher than the values in GOES-West. So that's a pattern that we saw in the flash extent density as well. And that may have something to do with being, slightly east of that 103-degree west line, but it's not always the case. Sometimes you're going to have situations where GOES-West might see more flashes than GOES-East, even if you are slightly east of that 103-degree west line. The 2022 hazardous weather testbed experiment showed a case study where the GOES-West and GOES-East GLMs observed very different flash and brightness values in that overlap region. And that may have been influenced by westerly wind shear attenuating light in a large optical depth before those lightning emissions reach the top of the cloud and then eventually reach the GLM. So if you've got westerly shear pushing a ton of hydrometeors out towards the east of the storm, and the GOES-East is looking from that eastward perspective, all those little hydrometeors, between the source of the light from the lightning and the optical sensor of the satellite, that may attenuate enough light to where the GOES-East GLM sees slightly fewer flashes than the GOES-West GLM, which is sort of looking at it straight on from that updraft side. So that's just one physical reason for why they may have different values in these situations. So I want to go back to our when our PDS warning was issued at 2024Z. So this is GOES-West on the left and GOES-East on the right, flash extent density. And the maximum, so right in the convective core, these values here, they increase from about 15 to about 50 flashes for both GLMs in that maximum pixel value. And that increase in flash density coincides with the onset of severe weather in the form of large hailstones and then also our tornado as well. So that coincides with a lot of literature which has been published on lightning jumps, where we have a sharp increase in lightning activity and correlated with an increased propensity for severe weather events. And even some research has shown that there's a really strong correlation between those lightning jumps and intensifying mesocyclonic updrafts, which is exactly the situation that we have in this case. So now shifting to the few minutes after. So remember, the PDS warning was issued at 22:24, and we had that tornado debris signature evident on radar by 22:29 Zulu. And interestingly enough, in this little 5-minute period here, both GLMs observed significant decreases in flash extent density despite the ongoing mature supercell and observed severe weather in terms of large hailstones and the ongoing tornado, which was confirmed by radar and weather spotters. So this is a bit of a complicated situation. There are many reasons which may explain this. Prior research has shown that lightning dives can occur during severe weather events like intense tornadoes, and there are many reasons why these may be observed. So they may be due to non-physical reasons. So again, it's like that situation where we talked about where you've got that large optical depth, that large field of hydrometeors, which is blocking the view of light from the GLM instrument. So it's not really it's a component that may not necessarily mean that there's actual fewer lightning flashes. So bringing in something like the ground-based networks or a local lightning mapping array, if you have that ability or capability near your office, like they do in West Texas, those may be good ways to confirm that the lightning activity is actually physically decreasing. So we always recommend to use those if you have them in conjunction with the GLM. But there also may be physical reasons for this phenomenon as well. So it could be that you've got changing dynamics within the thunderstorm. A few of the things that Rick and I talked about earlier was you've got a lot of research has shown that ingestion of slightly less buoyant air from the rear flank downdraft may be important for tornado formation. So that slightly less buoyant air may lead to slightly less charge separation and fewer lightning flashes being observed. You may also have something Rick mentioned was, especially once that tornado gets started, you're whipping up a ton of dust into the air, which is a big problem for your high plains offices, including Midland. And that dust, once it's being ingested into the mesocyclone of the storm, that may disrupt some of the mechanics that leads to the charge separation in that mixed phase region. It's just changing the composition or the chemistry of the atmosphere. And then also, kind of going hand in hand with the dust, maybe debris from the tornado being ingested into that updraft is also disrupting some of the charging processes that go on within thunderstorms. So there are many reasons why this may be the case, and I felt like this is a really interesting example of a pretty, clear-cut example of a classic supercell tornado where we do see this dive in lightning activity right after or right during the tornado occurrence. So one last thing I wanted to mention here is that I have done some previous work looking at the occurrences of all of the greater than or equal to 4-inch hailstones in the United States from last spring and summer. And this event actually had one of these 4-inch hailstones. So what this graph is showing here is that we have pretty similar values between GOES-East. So the GOES-East colors are the dark blue and the dark pink, and GOES-West colors are the light blue and the light pink. The blue colors are flash extent density. The pink colors are total optical energy. This red line is where the hailstone was observed, and the black line is the size of observed hailstones from the parent storm. So we've got our 4-inch hailstone here, and the GOES-East and GOES-West values for the maximum flash extent density. So I've reduced it down to a single number. So it's just the max, whatever the maximum pixel associated with the storm, that's what's being displayed for FED and TOE. They're remarkably similar from 30 minutes before the hailstone to 30 minutes after the hailstone. And we can see that in the 10 minutes, so this darker shaded region, in the 10 or so minutes before the hailstone was observed, we do see a strong increase in flash extent density and a pretty significant increase in flash extent density and an increase in total optical energy. But they also remain relatively elevated afterwards. And recall that was when the supercell continued to churn. So even though this 4-inch hailstone was observed, and we do see those increases, this supercell continued to produce severe weather after this hailstone. So just one thing I thought was interesting that I'd tie in here. So that's pretty much all I have to present on today. These are my references. If you'd like to go check them out, you can see the research that has contributed to this. And then I also want to thank you so much for inviting me back to the Satellite Book Club. I'm open to take any questions or comments. This upcoming severe season is a perfect time to refresh on the tools in the toolbox. Some of the main advantages from the GLM that we like to stress to forecasters is that you've got those 1-minute update times, so that you're going to get even for the fastest radar VCP of about 4.5 or 5 minutes, you're going to get 4 or 5 updates from the GLM in that time it takes to get a full radar coverage pattern. And the broad spatial extent of the GLM may be an advantage where in situations where you've got a radar outage or radar coverage may be poor, such as in mountainous areas. I'm always willing to make case study imagery for the ABI or GLM. If you work at a WFO, a region, a trading center, a cooperative institute, if you just want me to make something cool, you can always reach out to me. My email is there. My handle on X is there at Joseph Patton Weather. So reach out to me, keep the conversation going. And I want to end with saying how much I appreciate all the hard work of our friends at WFO Midland and across the Weather Service. You are valued. We care about your work very deeply. And thank you so much for giving me the opportunity to speak here today.
All right. Thank you, Joseph, so much for that great presentation, bringing back some memories that I had tried to repress from that event. But no, that I can attest, that was a beast of a storm. Our WFO is still repairing damage that was caused. We just got all of the windows replaced in our upper air building. We still have a pretty large dent in one of our panels of the radome from that event. So we'll continue to repair that and just in time for the next severe weather season, which is right on our doorstep. So thank you again, Joseph. I want to encourage everybody, please stay on for the discussion that we're going to have shortly. And if you'd like, you can change your meeting layout to tiled and select the hide tiles without video. Please submit your questions, if you have any, into the chat here on the Google Meet, or you can raise your hand and we can get to you verbally as well. One thing I did want to mention here for next week, a week from today, Thursday, March 13th, the same time, noon Eastern, David Hogg, a research associate from CIRO up in Norman, Oklahoma, will discuss examining the use of fire warnings during the February 2024 Southern Great Plains wildfire outbreak. So that should be a great presentation. And then I also want to encourage everybody, contact the Tower S team, Kashad and Emily, if you have any questions about the Satellite Book Club, or for configuration of satellite products. They've got a lot of great information, especially as we get into severe weather season. Some of us are already there. So it's a great time to look back, see what your configuration products are in the WFO, and look to them if you have any questions. All right, so we will dive right into the questions here. I think we've got our first question to ask. Let me get to that. And I did see a comment, Joseph, and I will echo this, that the numerical annotation is great. A lot of us forecasters, you know, we're looking at so many things very quickly during these type of events. And when you're able to see numbers increasing or decreasing, it really kind of helps with your mindset. Okay, I see the increasing numbers instead of maybe trying to figure out what the colors might be doing. So that's definitely great. We've got a question here from Sheldon. The observation that you saw with lowering flash values, but still severe weather observations, was seen over the years when we long ago used to manually estimate rainfall from satellite. Warming cloud tops did not necessarily mean immediate lowering of the max rain rates, just a comparison observation. Do you have some type of an average time of the weakening of the severe storm when you see the lightning flashes beginning to decrease?
Yeah, that's an interesting question, Sheldon. Yeah, you know, some research has shown those lowering flash values while that severe weather continues, but it's you know, I don't know that there's been an intensive examination of exactly how the timing works out between the weakening of the severe storm and when those lightning flashes begin to decrease. So I think that in this case, it's really just stresses that the GLM is a tool in the toolbox. So, you've got to use all the information available to you. If you still see a rip in supercell on radar and on ABI observations, but those GLM flashes are decreasing, that tells, you should be able to interpret that as a forecaster as, oh, the GLM isn't telling me this storm is decreasing in intensity. It's telling me something else. So what is it telling me? Is it telling me that, tornado may be ongoing? Is it telling me that there's hydrometeors attenuating the light? How can I use that information to better my conceptual understanding of how this thunderstorm is evolving? But if you see that, other lightning sensors, so the ground-based networks are also showing fewer flashes. If you see that, your radar reflectivities are dropping, or your velocity couplet isn't quite as tight as it was on previous scans, all those in concert with each other will tell a forecaster, okay, this storm is actually decreasing in intensity and maybe has a lower propensity for severe weather. But then also, like we showed in this case, even as that thunderstorm was dying and that updraft was collapsing, all those large hailstones that had been, roiling up there for hours potentially fell out, and you still had 3+ inch diameter hailstones being observed. So even if you do see some of those weakening signs, you may want to hang on to those headlines for just a few more minutes to cover those edge cases like that.
That's a very good point, Joseph. Thank you. Got another question, not necessarily a GLM, but about initiation for the storm. If you looked at, kind of before as it was forming, was there anything in the level 2 products from GOES, LI, maybe CAPE, that identified where initiation might be most likely?
I didn't specifically look at those products that you mentioned, Scott. Thank you for the question. But as Steve said later, that this was, a really great example of where you had an intersection of two outflow boundaries, one from the south, one from the north. We did have a severe storm. I didn't show this on here, but we did have a severe storm further to the south as this was happening. So you saw those collide right near the Midland WFO office, unfortunately, and then progress southward as it deviated to the right of the mean flow of the motion. And then, one of the thing that I wanted to mention too was I was just taking a look at surface observations, and you can see that the surface winds were coming from the southeast, to the south of Midland, and then really from the east to the north of Midland. So you've already got that convergence signal that you can see in the surface observation. So I think all of those together, this is, it might be something that, especially, Rick, with your experience, just sort of that intuition, you're like, okay, I can see all the ingredients here and I need to keep my eyes on this.
Yeah, definitely. I mean, we could see, obviously on satellite, the queue developing, we knew about the outflow, obviously a radar satellite. This was, I think, day 2 or 3 in a row that we had this exact same occurrence happen. But yeah, we could definitely see, even on, I had mentioned to Joseph on radar, these storms develop so quickly that even before we could see reflectivity on the lowest scan or 2 of the radar, we were receiving reports of baseball and softball size hail. So that's how quickly this thing developed and then barreled down to the south. Joseph, I did have a question or comment for you. So you talked about toward the end about the lightning decrease and some potential ideas for why that's happening. So have you noticed, and I know this is fairly new, you said there's not a lot of research on it. Have you noticed, if you've looked at other parts of the country, do you see something similar near tornado initiation or during the tornado? Because I know at the office, we observe the tornado live out the window, out the front door, and we could see a lot of dirt, a lot of dust that time of year, especially being drawn into the supercell, both from the inflow and the tornado itself. And so I was curious to see that, if that actually affected the lightning. It's interesting, a very interesting observation.
Yeah, I don't know exactly, the extent of the research that's been done on the lightning dives. There are some people who work at NASA Sport who have done a lot of research into that exact phenomenon. So I wouldn't be able to give you a great answer to say classify what regions or atmospheric conditions might lead to those lightning dives. But I do think that some of the reasons that we've talked about already, like the ingestion of the dust, which is a fairly unique occurrence for those storms that occur along the high plains. But you also have the advantage in those situations of having both GOES-West and GOES-East observations. So something that strengthened in my mind that this was probably a physical thing with the actual charging dynamics of the thunderstorm was that GOES-East and GOES-West, with those two different views, both observed the same phenomenon with those decreasing flash counts. So putting those two together, that like kind of like I mentioned earlier, you have to build this conceptual model of the thunderstorm in your head. So I wish I could give you a better answer on how to characterize those environments, but this definitely was something that we saw within this thunderstorm, and it definitely looked physical to me.
Awesome. I think we got time for one more quick question. So Kevin is asking, do you have any thoughts on why the TOE and FED remain level slightly increased after the 4-inch hail fallout from both GLMs? Wondering if that was from the thunderstorm intensity itself, the impact of decreased optical attenuation, or something else?
That's a really great question, Kevin. That was something that I was really trying to answer with my research that I presented on at AGU and AMS this year. I looked at all of the 4-inch or greater diameter hailstones from across the spring and summer of last year in the United States, and I tried to characterize them by tracking those FED and TOE values from the GOES-East and GOES-West GLMs, depending on if they were in that overlap region, I used both. If they were just in the eastern US, I used just GOES-East. And I was really looking for a pattern. If you sort of think it out, if you've got a lot of large hailstones, that may be attenuating a lot of light. So in my head, I was trying to think of, okay, well, maybe if you've got those large hailstones being observed, then you may see a slight decrease in the number of flashes or the brightness of the flashes, especially that was being observed before the hailstone occurs. And then after the hailstones fall out, maybe you see those numbers trick back up. And I didn't find a super strong correlation between those two things, but I did find something that was really interesting was that I did find strong statistical correlations in the near storm environment from the changing values of the storms. So, one thing that I brought in as well was I used SharpEye to bring in environment soundings and track things like moocape, precipitable water, LCL heights, etc. And I did find that there was, in environments where you've got much higher precipitable water values, so you can imagine that you have more of a chance for an HP supercell as opposed to a classic or an LP supercell. Those environments were associated strongly with lower TOE and FED values from these 4-inch hailstone storms. So, we didn't, I think that the explanation for why this storm in particular continued to show those elevated or increased TOE and FED values after the hailstone was, it had that classic supercell structure on radar for a long period of time after this 4-inch hailstone was observed. So despite any attenuation that may have occurred because of the large hailstones themselves, or from that shield of clouds spreading over to the east with the mean flow, I think that this storm still displayed those increased flash counts and flash brightness from both the GOES-West and the GOES-East GLM, which again adds credence to okay, these are what's actually being observed as opposed to something non-physical.
All right. Great questions, everyone. Thank you, Joseph, for presenting. Thank you, everybody, for attending. I'll pass it over to Brian.
Hey, Rick, thank you so much, Rick, for your facilitation today. I want to echo, as I think we all do, Joseph's comments about the extent to which we appreciate the work that your WFO and all the Weather Service field offices are doing. And Joseph, excellent talk. Thanks so much for bringing it to us. Always good to see GLM exploitation, especially multi-sensor, multi-product exploitations for high impact events. Really appreciate what you have done with Scott, and Steve Goodman was on the line as well. This is what we're seeing. These products are the culmination of years of work that have been done to bring GLM to the field and to the benefit of the forecast process. So it's really good to see the exploitation. And we're not done yet. Scott Rudlowski, I saw your invite to a discussion about settling upon the content for the LMX, the GeoXO Lightning Mapper, the follow-on to GLM, which is going to be even better than the current GLM, and look forward to engaging with you on that. As Rick told us a few minutes ago, please come back a week from today. David Hogg, Research Associate from Zero at the Cooperative Institute for Severe Weather out in Oklahoma. Week from today, examining the use of fire warnings during the February 2024 Southern Great Plains wildfire outbreak. We look forward to seeing everyone back here a week from today. And with that, we'll wrap up today's call.